Hello, in this video, I'll go over conducting a random forest analysis in R. I will provide a brief description of what random forest is, the R code used, how to handle missing data, how to interpret the output, classification and regression examples, and also discuss the strengths and weaknesses. Now, random forests, what are they? They're a popular non-parametric supervised machine learning algorithm for classification and regression. It was first introduced by Bryman in 2001, and there are many reasons why they're so popular. But one of the reasons is that it addresses a big problem with the use of decision trees, and that is overfitting. Decision trees comb through values and or categories among your covariates, also referred to as your features, to find the partitions that best predict your response. In other words, you're going through each of the features in your data set to find the best splits that predict your response variable. Now, the overfitting problem comes in when a model is very good at making predictions for a particular data set, but because it can be highly susceptible to idiosyncrasies specific to a given data set, its predictive power falls when new data are introduced. This is also referred to as low generalizability or the problem of high variance with decision trees. Now, random forest addresses this by employing the use of bagging. This involves bootstrap resampling of your original data set to form new data sets. The new data sets form are of equal size to the original data set because they're carried out with replacement, which can allow for the same observations to be selected more than once for a given bootstrap sample. So instead of one decision tree, you create a forest or ensemble of these decision trees. Additionally, there's not only randomness in the observation selected for a given bootstrap sample, there's also randomness in the features selected for a given tree, because only a subset of features would be selected as candidates at every split. This further differentiates the trees in the forest from each other, which in turn bolsters the generalizability of the model. So you may be thinking, wait, we're building a decision tree, but using a data set with duplicates. And on top of that, only a subset of our features. It sounds like we're making the decision tree worse. Now, random forest embodies the expression the whole is greater than the sum of its parts, each part being a specific decision tree. With random forests, our predictions are based on the aggregate of all the trees. For regression, it's based on the average, and for classification, it's based on the frequency. So by considering the aggregate and not the individual trees, we're essentially reducing the variance. So let's begin. I'm using the Pokemon dataset. This may not be the best dataset to use, but it's good enough for this demonstration. So I already have it loaded in the global environment. And the next step here is I'm using the dplyr package, and I'm basically leaving out some variables in the data set, and I'm using select, and I'm creating new variables. Basically, I'm turning type 1 into a factor, which is the type of Pokemon that, or rather the name of the Pokemon. And I'm also creating a new variable called combat power B. I'm basically dichotomizing the continuous variable combat power to high and low combat power. So if it's higher than 405, I'm setting it equal to 1, and that'll be high combat power. Else, it's just going to be low combat power, which I'm setting to 0, and this will be a binary factor. Okay, so let's actually run this code by first calling the package and then cleaning the data set, right? Okay, so the next step is I want to actually, after running it, the next step, I want to split my data set. We can split the data set into train and test using an 80-20 split. One thing to note, according to Bryman in 96 and in 2001, as well as several others, is that specifically for the out-of-bag error, which I'll go over when I discuss random forest output, it removes the need to set aside a test set. However, out-of-bag error is built into random forest, while test train split is a general method for model evaluation, which can be used to evaluate how other algorithms that are not random forest compare. For example, your logistic regression, your neural nets, etc. So you can still go ahead and use a test train split. Just be careful to follow best practices and be forthcoming about all the different models or modifications used on a test set. Results you get from a test set that inform decision making to modify or select a particular model could result in overfitting as well, uh, especially if the test set is used more than once. Okay, so we'll first start by setting seed for reproducibility since randomness is involved. Then the next step right here is I'm creating a new field called Pokemon ID. I'm basing it on the row number, and there's like 151 observations. So after that, I am basically sampling randomly 80% from that Pokey data set and calling it, and that'll basically be my train data set. Then what I'm doing is all the observations that were not included in my train data set that were in the original Pokey data set, I'm going to use the anti-join function to pull those out, the remaining 20%, and call it my test set. And now, since I don't no longer need the ID field because I used it just for the anti-join and I no longer need it, so I'm just setting it to null. So I'm just taking it out. Okay. So before we jump into the actual running the random forest and the analysis. Before we start doing that, we can go on a little side quest and explore what happens if we were to have hypothetically missing or NA values in our data set. First, let's add NA values to this data set. So the first step is we're creating a new data set called train underscore NA, and it has HP missing when the Pokemon type is either ice or ghost. So we're creating this new data set right here, train underscore NA. Now, there are several, just to take a quick step back, okay, there are several ways to handle missing data, and we'll just go over a few in this video. The first two are quick fixes and the third one is a bit more involved that I'll cover. When dealing with missing data, it's always important to know why your data are missing. For example, how reasonable it is to assume your data are missing at random. Also, is missingness due to other variables, etc. In addition, you should also consider the proportion of your observations with missing data. Yeah, you can do a whole course on missing data, and for this video, I'm just covering just a few methods. Now, these methods are available in the random forest function. So when we go to run our random forest analysis, we would be using this random forest function, and one of the arguments is what to do with NAs if NAs are present. The default is na.fail, which means that the NAs, essentially the model will not run if there are NAs present. So you have to pretty much do something with it. So the next option, what to do with this is NA omit, which is one option, which is simply we're just going to ignore uh, or take out all the observations that have at least one NA present. So that's one way to handle missing data, right? The second way is to use the or set na.action to na.roughFix right here. So what this does, it replaces NA values with the median value for the continuous variables or the most frequent value for if the variable is a factor. However, some simulation studies have suggested that this can lead to inaccuracies, hence the name rough fix, which is suggesting that this approach is leaving something to be desired, right? So there's the third option that I'll cover is to use train, uh, which is to use the function rf impute, which is available in the random forest package. So if the first step is to actually install the package. Once you've done that, you can call random forest. And because RF is a random method, we're going to set C for reproducibility. And we're going to just take a look at what we need for the RF impute function. Again, we're using the train underscore NA data, and we're trying to impute missing data. So what you're essentially doing, well, okay, but what's going on? That's the first thing. Well, what is RF impute doing? So the first step is that it basically generates initial estimates for NAs using na.rovfix. Then the random forest algorithm is used to generate or compute a proximity matrix. A proximity matrix is a square matrix consisting of values for each pair of observations, representing how similar they are. Hence, the number of rows and columns in a proximity matrix is equal to the number of observations in our data set. Remember, random forest is comprised of hundreds of decision trees. Each decision tree moves observations in a given bootstrap sample through a set of nodes representing various splits for variables in our data sets. So this can be illustrated via some flowchart where the observations all end up in a set of leaf or terminal nodes attempting to represent values in your response. The proportion of times a pair of observations end up in the same leaf or terminal node across the decision tree is how similarity between the observations is defined. These values will range from 0 to 1 in the off diagonal and 1 in the diagonal. The purpose these values serve for imputation is that they're used to update the values from the initial na.roughfix to give similar observations more weight when attempting to impute the missing data. To find missing data for continuous variables, a weighted average is used. For categorical variables, the category with the largest average proximity value is selected. This process is iterated a set number of times using the new imputed values. In the RF impute function, you can see we're essentially doing is first we're setting our response variable name, which is combat power B. The number we're also setting the data set. Remember, we're using the train underscore NA data set. We're setting the number of iterations to 5, and we're setting the number of trees that the forest generates to 500. The default is 300. So let's run this. Okay. Now we get the output, and what it's showing in the output, each row represents an iteration. The columns represent what is happening to the error at each iteration. The first column is the out-of-bag error. The second column, 1, is the class-specific error for the negative class. In this example, it would be the category 0 for low attack power. And the third column, called 2, is the class-specific error rate for the positive class. In this example, it would be the category 1 for high attack power. Now, while this sounds foolproof, nothing really is. Again, I must reiterate that the reason why your data are missing and how much of it is missing should be the deciding factor whether it makes sense to use this method. Additionally, Bryman warns that the out-of-bag error estimates may be optimistic when employing imputation on your data set. So, okay, we can also, again, because this is a what if scenario, is actually just check the NA imputed values and compare it to the original values. So let's look at the imputed values. Remember, we set HP missing to the Ghost and Ice Pokemon, and here they are with the imputed values for HP. And now let's compare it to the actual values in the original train data set. And we can sort of see that they're a bit far, well, they're close. I wouldn't say far off completely. They're a bit off, but not far off, right? So, but it's serviceable in a sense right here. Okay. And but since we already have the data, this was just for a demonstration. But since we already have the data, it will just go ahead and use the trained data set and not this new data set with imputed values. Okay. So yeah. So now let's actually finally fit or rather conduct our random forest analysis using the random forest function. I already called the package random forest, so I can go ahead and use it. Uh, since also bit by bit, we can go where I'm setting seed because randomness is involved, and I'm doing that for reproducibility. Combat power B is our response variable, which is a binary factor. Therefore, this will be for classification. Make sure to set your response to a factor. We're using a dot to indicate to use all other columns other than the response, but the trained data set itself would only include columns 3 to 9. Next, you should make note of the default arguments for your hyperparameters. First is the entry argument, which is the default is set to 500. This is the number of trees in your forest. Generally, the more trees, the better that your model will perform until it begins to plateau around a few hundred trees. Another hyperparameter you should consider is M tree. The default value for classification random forest is the square root of P. P is equal to the number of features in your data set. This determines the number of features that can be selected as candidates at each split. This is how the trees are differentiated from one another besides using the bootstrap sample itself, since each bootstrap sample would sample different observations. Now, and the randomness is that since each split is only on a subset and not all the features in a data set are considered. Another hyperparameter is the node size, I should say, which represents the minimum number of observations for a terminal node. The default for classification is 1. So what does this mean? Remember, decision trees split observations in a data set based on certain conditions, which can be visualized as a flowchart of nodes. For example, consider a node that checks if a Pokemon's HP is greater than 50. If the answer is yes, the observations move to the right. If no, it moves to the left. This process may continue with subsequent splits on the same or different features until the observations reach a terminal or leaf node, which represents the value of the response variable. However, if splitting a feature will result in two nodes where one of those nodes is less than the minimum node size that is set, then it is not split, and that node becomes a leaf or terminal node. Therefore, larger values of node or of the actual node size that's used will result in smaller trees due to fewer splits possible, and smaller node size values will result in larger trees. This is known as your tree depth. If we consider only a single tree, allowing it to split many times can lead to high variance and lead to overfitting, but smaller trees could lead to high bias and underfitting. Again, another default argument is it's already set is NA.action is equal to NA fail. Since we don't have NAs, the algorithm will not fail. I also included proximity is equal to true, that argument, which can be excluded. I just want to compute the proximity matrix just to show it since I mentioned it earlier. I also set importance equal to true. For classification, this will ask to compute the mean decrease in accuracy for overall categories in your response, along with the mean decrease in Gini. You will also get the mean decrease in accuracy for the class-specific measures computed, and I'll go over what this means when I discuss importance. There are also other arguments, of course, that you can adjust in the function, but I just wanted to cover a few. So let's actually run the model finally. So again, set that C for reproducibility. We ran the model. And now let's look at the output, as you can see in the console. And you can see here that it confirms that this is a classification response. The also it confirms the default number of trees, the default features selected, and also our out-of-bag error rate. So what is this out-of-bag error? Because I've been talking about it, right? But I haven't really described what it is. Remember, I said that the bootstrap sample includes duplicates. Consequently, some observations are left out and not selected. Typically, about a third of observations are not included in the bootstrap sample, and we can move those observations through decision trees that were not built using them. Each decision tree, those observations are moved through, provide a vote for a predicted response value for the observation. These votes are then tallied to determine the majority vote for the predicted response value. And the out-of-bag error rate indicates how often those predicted response values didn't match the actual response values. For our model, the outer bag error rate is it's right underneath 10%, which is pretty good. It's about 8.26, it's 8.26% exactly. And it also provides a confusion matrix, which provides the actual by predicted classification. The diagonal is the correctly classified versus the off diagonal is the number of observations misclassified. There's also the class-specific error rate. This could show if it could be useful, I should say, if a particular response category was misclassified more than the other. But as you can see here, both error rates appear pretty close. Now, generally, what we want to see is a low out-of-bag error because this would indicate that the model is not over or underfitting and has good generalizability. However, what value should be considered as low? Uh, because I just said low, but what value does that mean? What does low out-of-bag error rate mean, right? And to answer that question, that depends on several factors including the complexity of the model and or data set. You may also, another useful thing to do is simply research and find out how other models performed on similar data sets, compare. So that's one route you can go by. However, if you just want a rough rule of thumb, which may not always be appropriate, uh, there have been some people who have suggested that anything below a 10% can be considered low, and 10 to 20 is somewhat more moderate error rate, but you want it as low as possible, of course. But now, this may not be the best way to think about it. And a better way to think about it is, well, if you get an out-of-bag error of 50%, that would mean your model is misclassifying at 50%, or rather, it's misclassifying 50% of the out-of-bag samples. And your model is no better than randomly guessing. There could be several reasons why you may have gotten a 50% error rate. You may need more observations. You should also take a closer look at the features, make sure everything's correct that you selected to use in your model. But that's a better way of going about thinking about it. Okay. So since I set proximity is equal to true, I asked the function to compute the proximity matrix. And now I'm just going to set it as a data frame. And now let's actually just view it and it should pop up. So yeah, and this is essentially, I just wanted to show what it looked like. As you can see, it's a, proximity matrix. If I hover over my arrow, right here, it's showing it's 121 by 121 matrix representing the number of observations in our data set. And they're ones in the diagonal, and the off diagonal represents each number representing a specific observation, and each pair, and the off diagonal represents how the each observation, how similar it is to other observations. But I just wanted to just show it. Now let's actually talk about importance. So as you recall, I also set importance is equal to true, and it calculates and stores variable importance measures based on the mean decrease in accuracy. Now, a byproduct of random forest is the ability to evaluate feature importance, also referred to as the variable importance measure or VIM. You can use the function importance, also available in the random forest package, to see how features in your model compare based on predictive power. So let's take a look at that. And I'm right here. Basically, I'm using the function on our model. So one thing to note, there's also a type argument in the function with two options being one or two that you can use, but I already set importance to true, which will give me both. Method one uses the mean decrease in accuracy. You need to have set importance is equal to true to actually, for the random forest function to compute this. So to understand how accuracy is measured, recall that each tree is trained on a bootstrap sample, and observations not selected for training will make up the out-of-bag sample. The values for a feature in a tree are permuted. In other words, change in the out-of-bag sample, which in turn disrupts the relationship that the features will have with the response. Predictions of the response are then made using the permuted features, and then it is compared with the predictions with the original values. The difference in accuracy is taken for each tree, and those differences are averaged and then normalized using the standard deviation of differences. This is then done for each feature, and the mean decrease of accuracy for each feature is compared. Features with the largest mean decrease in accuracy are considered to be the most important. The thinking is that features more impacted by permutation of the values should be considered to be more important than a feature less impacted. Now, type 2 is the mean decrease in node impurity. Impurity is a measure of how mixed a particular split is at predicting the response. In other words, if a split on a specific feature and threshold value results in capturing only observations with a particular value on the response, then the resulting node would be considered pure. However, if there's a mixture of observations in the same node with different values for the response, it would be considered impure. The proportion of observations with different values in the response from a resulting split is the main component of how impurity is measured. In decision trees, the selection of features and threshold is based on the reduction in impurity, which is the difference in impurity before and after a split. Typically, to measure reduction in impurity with decision trees, the Gini index is used. Therefore, a feature with a very large or large decrease in impurity would be considered important. The reduction of impurity is the total decrease in node impurity for a particular feature averaged across all decision trees, all decision trees specifically that the feature was used in. This is done for each feature, and the features with the highest mean decrease in node impurity are considered to be the most important. The mean decrease in node impurity is generally less preferred because it has been shown to be more biased when features have many options for splitting. For example, categorical variables with a large number of categories or continuous variables. However, there are times when the mean decrease in accuracy can be less preferred. For example, when dealing with high dimensional data, the mean decrease in purity was shown to be more robust at handling deviations in data than the mean decrease in accuracy. So, so that's just the comparison. And let's actually plot what this looks like. Oh, I should also mention the first initial columns are the class specific mean decrease in accuracy, 0 and 1. Then you mean the third column, mean decrease in accuracy. That is the across categories, and the mean decrease in Gini is provided. But let's actually rank order it. We can actually rank order it and plot it using the var imp plot function by looking at the model and sorting it. And let's do that. So yeah, and what it does, and this what it's showing right here is it's illustrated via a Cleveland dot plot, and it rank orders which variables are most important, and it does it side by side, one for the mean decrease in accuracy and the mean decrease in Gini. And you can see for the most part, they're very similar. As when it comes, speed defense was ranked highest as deemed as the one with the highest predictive power of the response, or in other words, the most important. So now, one thing to note is that, okay, I'm using this word important. However, it's important to note that with either measure of importance, they do not tell you anything more than the strength of a feature at predicting the response. Well, we don't get insight into the direction or the pattern. If you do want information about direction or pattern of a relationship a particular feature has with a response, then you can use the partial dependency plot or PDP. These PDPs are model agnostic, meaning you can use it for other machine learning algorithms other than random forest. They allow us to pick out a feature and evaluate its main effect on our response. They generally work by changing values for one feature to some constant value across all observations without changing any of the other features and taking the average predictive probability across all observations. Then for the same feature, you change all the observations to a different value and set that as the constant to get the average predicted probability across observations. You do this for all the values in the feature of interest to build your PDP. So let's actually run it and see what it looks like. Uh, I'm using the partial plot function in the random forest package. I'm setting the model name. I'm also using the trained data set. And also in this example, I am setting the variable X variable because I'm looking out of all the features which one I want to observe. And I'm also setting which class. This is for classification and allows you to indicate which category on the response you want to focus on. The default selected is the first class on our response, which would have been 0 anyway, but I'm just setting it so you are aware that you can adjust it. And right now, so let's run it. Oh, wait. There's a mistake right here. I have to take the prob is equal to true shouldn't have been there. That's something else. Yeah. So yeah, just ignore that. But basically, if you run it again, you won't get that error message and you'll get the same plot. Basically, I included an additional argument that should not have been included. Basically, the partial plot function draws our PDP. And so let's consider, okay, how should we be interpreting this plot? Well, first is that if we were to observe hypothetically a horizontal line from 0 on the y-axis across all the entire range of values of our feature, in this case, the on the x-axis, which is speed, this would mean that there's no observed main effect of the feature and the response. So, but right now, what this plot specifically is showing is that the y-axis, it's the scale for the y-axis, you should note, is the centered logit transformation, and it's not the probability scale of the response. And so you have 0, you have positive values, and you have negative values. To interpret the positive and negative values on the y-axis, you must consider which specific category in our response we're predicting. And now remember, we set it to 0, which is low attack power, and that's essentially what we're predicting. Negative values indicate that low attack power, in other words, 0 on our response, is less likely for those values on the feature speed. And positive values indicate that low attack power is more likely for those values of the feed on the feature, which is speed. So what we can interpret it as is we see for the values over 80 on our feature speed, it does not predict low attack power as opposed to values under 80, right? So you can also observe some small, if you can see the cursor, small vertical lines on the x-axis. These are representing deciles. It gives you a sense of how observations are distributed across a range of values. 10% of the observations have values below the first vertical line, uh, line like right before 40, and 90% of observations seem to have values under 110 on our feature right here. This is like about 110. So 90% of the observations have values below that. Generally, you do not want to see extreme skewness to one end, even though we are using a nonlinear model because we would have more uncertainty about observations with outlier values. So as you can see, these PDPs are pretty good, but they are limited. And the limitation is that we're assuming features are independent here. In other words, if there are interactions with the effect a feature has on the response, so in other words, interaction meaning uh, the effect that speed would have on attack power, it depends on the value of another feature that won't be picked up by the PDPs. In addition, because PDPs plot aggregated information, specifically the average partial effect on the predicted response, there could be a lot of variance among predicted responses for specific values of your feature compared to other values of your feature, which is ignored when you're just considering an average. In fact, you can have a feature where the average across values appear to be zero, indicating no main effect. But if you were to disaggregate those values and plot values for each observation, a pattern can emerge that would suggest a relationship. Generating a disaggregated plot can be done with individual conditional expectation plot referred to as ICE plots. I can do a separate video just going over PDPs in more detail and also ICE plots using other packages. But for now, just understand that these PDPs are limited. Now, moving on to model accuracy, right? So now the main reason we're using RF, random forest, is to make predictions, right? We were already able to evaluate our model using the out-of-bag error, but we can also evaluate it with the more general method. We can take our predicted values for each observation and match the accuracy by comparing it to actual values in our train and test sets. We can use the confusion matrix function from the caret package here. First, let's measure accuracy of the model we trained on our training set. First, well, actually, let's load the call the package and do predictions. Now we've basically generated the predictions. Now we're going to use the confusion matrix function to compare the predicted to the actual values in our train set. And we sort of get a lot of output. So let me just increase the size. Okay. Now the output shows for this confusion matrix, the rows are the predicted class and the columns labeled reference is our actual data. Next is the accuracy score in this case. So, and that's essentially the main thing, which is perfect. Of course, we expect a very high accuracy for the training set. However, perfect accuracy could suggest overfitting. The 95% confidence interval. It's a measure of uncertainty around our accuracy. Uh, the next bit of information is the no information the no information rate. This is the proportion of the largest category for our response. Next is the one-sided hypothesis test. And that is the one-sided hypothesis test. It's pretty much it's used to conduct to see whether our overall accuracy is greater than the rate of the larger category. So this comes in handy when there is more values for one category compared to others in your response variable. You do not want to see a model accuracy that is close to or below the no information rate. Here we see the p-value is very small, indicating that we can reject the null hypothesis and accept the alternative there that our accuracy score is significantly greater than our no information rate value. The next thing is the kappa statistic K, which is a measure of the agreement between the actual and predicted. In other words, how much better our model is than just guessing. Values close to 1 indicate high agreement between the actual and predicted, but values close to 0 suggest our model isn't any better than guessing. So for the rest of the values, I can do a whole separate video focused on categorical data analysis, explaining each one and when they may come in handy. I think I discussed some of this in a past video with the logistic regression, but for now, we really just wanted the accuracy score, the specific value, and we can also more interesting is the finding predictive scores and now evaluate using comparing it to the actual test set, our predicted values, um, or rather fitting our model onto our test set, generating the predictive values and comparing the actual versus predicted on our test set. And this is the accuracy score, which is very high, 93%. Yeah. And yeah, so next, and that's how we evaluate our model in that way. So let me just pull this down just a little bit since we don't need any more. And now let's actually go in. Now let's run a random forest for regression. Now the response variable we're using is the original variable combat power as a response variable, which is continuous, and we are essentially including most of the fields in the data set as features. Keep in mind that not all the default arguments for regression will be the same as for classification. Note, I'm leaving out we're using the same training data set, but I'm leaving out the binary categorical transformation of our response variable from this. So that's one thing. I'm also setting importance is equal to true for regression because I want to compute the percent increase in mean square error along with the increase in node purity. And let's set seed and run our model. We're calling it RF2. And let's look at the output. So looking at the output in the console, it confirms we're confirming that we are indeed running a regression. And as you can see, the number of random variables that are randomly sampled as candidates at each split, it's even though it's computed a bit differently, now it's the way to compute it is the number of predictors divided by 3 instead of the square root of p as we did with classification. Also, the default node size is a bit different. We discussed earlier, then before for classification it was 1, now it's 5 for regression. Now you can also just check the package description and like just review it, but those are the main hyperparameter differences between the regression and classification adjustment. And looking at the output now, it confirms even though the formula used to compute or decide on the number of candidates at each split that should be selected, that there, even though those values are the same, the formulas were different to get there. Now we no longer have, if you notice, we no longer have an error rate, but a mean of squared residuals. You can refer to this as the mean squared error, Remember, since the response variable is continuous, we are taking the squared difference of the actual response value for a given observation and the mean of the out-of-bag predicted response values for that observation and averaging it across all observations. The lower our mean squared residual, the closer our model is at predicting the response. The percent of variance explained is 1 minus the mean squared residual over the variance of the response. This is also referred to as a pseudo R squared because it's not defined in the same way as it is with linear regression. Keep in mind we're using this ensemble method, but it's still you can still evaluate use it to evaluate how your model compares to other models. Now, so that's interpreting the output. Now let's actually look at the importance. So let's run it again, and you'll notice when we use the importance function on our regression model, uh, let's actually also just look at the plot at the same time too. Looking at the values for importance and the plot, and let me lower this just a bit just so you can see the values for importance. We're same as before, we're looking at out-of-bag cases before and after permuting the values, but now we are measuring the average increase in squared out-of-bag residuals. For the second type, we are also looking at node impurity, but instead of the Gini index, which we use for classification, we're using the residual sum of squares. Now, to evaluate now we can just go to the next step and we will evaluate the accuracy on the training and test sets. So here, one approach is there's a few things you can do. One of them is simply, which I selected here, is to take the average squared difference between the predicted and actual values, which is the mean square error. Here I'm calling it MSE. The smaller the value, the better the model is at predicting. You can use this value to compare to other models on other test sets. So same as before, we have predicted values on our we're comparing the predicted versus the actual values on our trained data set. First, we're computing these predicted values, and then we're generating our mean square error on our trained data set, and it gives us a specific value. And now we're doing the same for our test data set to get that mean. And now we're doing the same thing for our And now we're doing the same thing for our test data set. Okay, and you get the mean square error for the test data set. Again, you can use that to compare to other models. The smaller, the better your model is at predicting. In conclusion, the strength of random forest algorithm is that they work really well for structured data sets of lower high dimensionality. Generally, you could think of lower high dimensionality as the number of your features in your data set as it compares to the size of your data set. They have been shown to outperform parametric models, your logistic regressions, and so forth. And they do not have these distributional assumptions such as heteroscedasticity, linearity. They also perform really well in competitions. And they're also referred to as these black box algorithm because it has a strong focus on prediction over interpretability. But as we discussed, you can get some insight about features through these variable importance, and that's an advantage random forests have over other machine learning algorithms because variable importance it measures, or rather, it allows us to rank order our variables based on importance, and it's very helpful in picking out important features and also can be used for feature selection. In addition, they do not require much hyperparameter tuning as other algorithms, and the default settings often work very well. Also, you do not have to worry about units of measurements, of the features or having to scale them. But random forests are limited. There's sometimes the algorithms may inflate the importance of categorical features with many levels or continuous features, or more specifically, categorical variables with many levels, and separate from that, also continuous variables or features, because it's more likely to run across a level or value that has an impact on the response when there are a lot more of them. And also to consider no algorithm is perfect, and it's often good practice to try and understand your data as much as possible. So some algorithms basically might work better for certain data sets than others, and there's not this one algorithm that is best among all of them, right? So that being said, random forest, because of its ease of use coupled with its predictive power, is an important tool to have in your toolbox, right? So yeah, this video is just meant to cover ways you can get started with random forest. I'm just scratching the surface with random forest. You can go more in depth with your random forest algorithms. Even though I mentioned the default hyperparameter settings work well, there are functions you can use to tune the hyperparameters. In addition, there are also extensions to random forest like weighted forest, online forest, survival forest, just to name a few, that might be more appropriate for certain data sets. There are also unsupervised, a variation that using proximity matrix of you can use them for unsupervised machine learning as well. So yeah, overall, I hope you found this video helpful and take care. Bye.